Welcome to the deep dive. Today, we are taking a bit of a shortcut, really. We're diving into the absolute fundamentals of understanding any data set. Descriptive statistics.
Hmm.
You know, whether you're looking at test scores, company salaries, maybe coffee sales figures. These tools we're talking about, mean, median, standard deviation, they're essential. They help you make sense of it all fast.
Exactly. Because raw numbers, they're just noise
Right.
until you put some structure on them. So our mission today is really practical. We want to cut through the jargon, get straight to the core ideas. We'll look at how you measure the center of your data, how spread out it is, and if different pieces of data are, connected somehow.
And crucially, not just what these measures are, but when you should actually use each one. That's key. Because choosing, say, the mean over the median, or deciding if standard deviation tells the whole story, that choice shapes the narrative you get from your data. So let's jump right in. Where do people usually trip up first?
Okay, finding the center, or central tendency, as it's formally called. Most people jump straight to the mean, the average. Add them up, divide by the count. But just assuming the mean is the best measure of center, that's often where the trouble starts.
Yeah, we all learned that calculation in school. Scores like 70, 80, 90, dead simple. The mean is 80, perfect center. But real-world data isn't usually that neat, is it?
Yeah.
There's always that one weird number, the outlier.
Precisely. And the mean is super sensitive to those outliers.
Yeah.
Extremely sensitive. Think about average income on a street. You have 50 regular houses, and then one billionaire builds a huge mansion. That one mansion, it drags the average income way, way up. Suddenly, the average doesn't represent anyone who actually lives there. The mean just can't handle that kind of skew well.
Right. Which brings us to the median. The statistician's secret weapon, maybe? It's the value smack dab in the middle when you line everything up in order. It doesn't care how massive that mansion is or how tiny another value is. It just looks at the middle position. Odd number of points, it's the middle one. Even number, you average the two middle ones. Simple.
It's robust. That's the term we use. Robust against outliers. That's the key insight here.
Okay, let's make this concrete. The source material had that great comparison, the Class A and Class B scores.
Ah, yes. Class A was beautifully symmetrical. Let's see, the scores were 65, 70, 75, 80, 85, 90, 95. Calculate the mean, you get 80. Find the median, it's also 80. They match perfectly. No skew.
Okay, nice and tidy. Now, Class B introduces a curveball. The scores are 45, 70, 75, 75, 80, 85, 95. See that 45? That's way lower than the rest. It's our outlier.
Right. And watch what happens. The mean for Class B gets pulled down by that 45. It drops to 75. But the median, the middle value when ordered, that's still 75.
Wait a second. So in Class B, the mean is 75 and the median is 75. They match again. Doesn't that mean the mean is okay here too?
Yeah. Not quite. It's subtle. The fact that the mean dropped from 80 in Class A down to 75 in Class B because of that one low score, that tells you the data is skewed. The mean was affected. It moved. The median stayed put relative to the bulk of the data. So while they numerically match in Class B at 75, the median 75 is the more honest reflection of the typical student score in that skewed set. The mean, also 75, confirms how much that outlier distorted the overall picture compared to Class A. You always need to compare them.
Got it. So for things like income or house prices, where you often get extremes, the median is usually the safer bet. It tells a truer story of the middle.
Definitely. Then there's the third measure of center, the mode. Often overlooked. It's simply the value that shows up most often. In Class B, the score 75 appeared twice, more than any other score. So 75 is the mode. Class A, remember, 65, 70, 77, no score repeated. So Class A actually had no mode.
Okay, so mode seems useful for categorical data, like favorite colors or maybe discrete numbers. But you mentioned something interesting earlier. What if there's more than one mode?
Yeah, that's where it gets really interesting. If you have multimodal data, two or more values appearing with high frequency, say you do a survey asking for satisfaction on a 1 to 5 scale, and you find lots of people chose 1, very dissatisfied, and lots chose 5, very satisfied, with fewer in the middle. That's bimodal data, 2 peaks. Or maybe 1, 3, and 5 are all popular. That's multimodal. What that tells you often is that you're not looking at one single group. You might have mashed together data from 2 or 3 distinct populations with very different views or behaviors. Big red flag for analysis.
Okay, so we've got a handle on the center, mean, median, mode. But knowing the center isn't enough, is it? Like your desert example. An average temperature doesn't tell you about those wild swings from day to night. We need to measure the spread, the variability.
Absolutely critical.
Yeah.
Variability tells you about risk, about consistency, predictability. And the first step towards measuring that spread is usually calculating the variance. The idea is to find the average distance of each data point from the mean.
Right. So you take each value, find how far it is from the mean, that's the deviation, and then You square that difference. Why do we square it again?
Good point. We squared for a mathematical reason. If you just added up the differences, the points above the mean, positive differences, and the points below the mean, negative differences, would cancel each other out. You'd always end up with 0, which tells you nothing about the spread. Squaring makes all those differences positive, so they add up meaningfully.
Okay, that makes sense. But squaring creates a new problem, doesn't it? If we're measuring, say, salaries in dollars, now our variance is in squared dollars. What even is a squared dollar? It's hard to interpret. Like that data set 1 example, variance is 8. What does 8 squared somethings mean?
Exactly. It's not intuitive at all, which is why we almost immediately take the next step, standard deviation, or SD. You really take the square root of the variance. That's it. And magically, that gets you back to the original units. If you started with dollars, the SD is in dollars. If you measured height in centimeters, the SD is in centimeters. Much better.
And the standard deviation gives us a sort of standard yardstick for spread. Like how far things typically stray from the average. We hear about that 68% rule, right?
Yeah, that's for data that follows a nice bell curve, a normal distribution. About 68% of your data points will fall within one standard deviation wiggle room, either side of the mean. About 95% within 2 SDs. It gives you a really good feel for how tightly clustered the data is around the average. It's powerful.
Let's use those 2 data sets again. They really highlight why SD matters. Both have the same center, remember?
Right. Data set 1 was 10, 12, 14, 16, 18. Nice and tight. The mean is 14.
And data set 2 was 2, 8, 14, 20, 26. Same mean, 14, but look at those ends. Much wider.
Okay, now the SD. For data set 1, the tight one, the standard deviation is low, just 2.83.
Makes sense. The numbers are close together.
But for data set 2, the spread out one, the SD, jumps way up to 8.49, nearly 3 times higher.
Wow. So even with the exact same average, data set 2 is way more volatile, less predictable. If that was, say, investment returns like you mentioned, Fund 1 looks much safer, even though the average return is identical. SD shows you the risk.
Precisely. It quantifies that risk or variability.
Yeah.
But there's another catch. What if you want to compare variability between things measured on totally different scales, like comparing the variability in CEO salaries, millions of dollars, with the variability in the price of eggs, a few dollars?
Yeah, the standard deviation for CEO salaries would be huge in absolute dollar terms, but the SD for eggs would be tiny. Doesn't seem like a fair comparison.
Exactly. For that, we need a relative measure of spread. That's the coefficient of variation, or CV. You calculate it by taking the standard deviation and dividing it by the mean. Then usually express it as a percentage, SD divided by mean. It basically tells you how big the spread is relative to the average. It cancels out the units.
Okay, let's use that company salary example. It makes it clearer. Company A, mean salary $50,000, standard deviation $5,000.
So the CV for Company A is $5,000 divided by $50,000, which is 0.1 or 10%.
Right. Now, Company B, higher average salary, $100,000. And a higher absolute spread, too, an SD of $8,000.
So just looking at the $8,000 SD, you might think Company B has more variable pay. But calculate its CV, $8,000 divided by $100,000. That's 0.08, or only 8%.
Uh-huh. So relative to its higher average salary, Company B's pay structure is actually less variable than Company A's 8%, in Reed's case is 10%. Even though Company A's dollar spread was smaller, 5K versus 8K, that's clever, CV is essential for comparing across different scales or means.
Indispensable for those kinds of comparisons.
Okay, we've covered center, we've covered spread. What's left? Well, often data doesn't exist in isolation. We want to know if 2 different things are related, how they move together.
Exactly. We need to measure the relationship or association between 2 variables. And the primary tool for starting that investigation is covariance. It's a measure of how 2 variables change together. Do they go up together, or does one go up while the other goes down?
How does it work? Sounds a bit more complex.
It involves looking at pairs of data. For each pair, you see how far each value is from its own variable's mean. Then you multiply these deviations together for each pair and average those products across all the pairs.
Okay. Multiply the deviations. So what does the final number, the covariance value, actually tell us?
Mostly, it tells us the direction of the linear relationship. If the covariance is positive, it means when one variable tends to be above its mean, the other variable also tends to be above its mean. They move in the same direction. If it's negative, they move in opposite directions. When one is high, the other tends to be low.
And if there's no real connection, like, maybe my height and the price of tea in China?
Then you'd expect the covariance to be close to 0. It suggests no linear relationship. Now, important point. Zero covariance doesn't automatically mean no relationship whatsoever, just no straight line relationship. Could be a curve or something complex, but it rules out the simple linear link.
Let's use the example. Hours studied versus exam scores. That feels intuitive. The data pairs were hours 2, 4, 6, 8, 10, and scores 65, 70, 80, 85, 90.
Right. You run the numbers, calculate the covariance for that specific data, and you get a positive value, 32.5.
Positive. So that confirms what we'd expect, right? More hours studied tends to go with higher scores.
Exactly. The positive sign confirms the positive relationship. More study, higher score. But, and this is the limitation of covariance, what does the number 32.5 actually mean? Is that strong, weak?
Yeah, I was wondering that. It's not obvious. Like SD was in dollars, CV was a percent. What unit is 32.5 inches?
It's in hours times score points, not very helpful. The magnitude of the covariance depends on the units of the variables themselves, so you can't easily compare a covariance of 32.5 here with a covariance from a different pair of variables measured differently. It really only reliably tells you the direction, positive, negative, or zero.
So if we want to know the strength of the relationship, not just the direction.
Then you need to take the next step, which is calculating the correlation coefficient, usually denoted R. Correlation essentially takes the covariance and standardizes it, scaling it down so it always falls between -1 and +1.
Ah, okay. So -1 is a perfect negative relationship, +1 is a perfect positive one, and 0 is no linear relationship.
Precisely. Correlation gives you both direction and strength on a standard, easy-to-interpret scale. It's usually more useful than covariance alone.
Yeah.
Hashtag tag out a relationship.
Okay, let's pull this all together. We've covered the tools to find the center, mean, median mode, measure the spread, variance, SD, CV, and understand relationships, covariance leading to correlation. These aren't just abstract math concepts, they are the tools you use to build a story from your data.
Right. Let's apply quickly to that coffee shop example. Weekly sales data. You see sales are pretty steady Monday to Thursday, maybe 110, 125 cups. Then boom, Friday hits 100, Saturday 200. But Sunday drops off a cliff to 90.
Okay, lots of variation there. If the owner just calculates the mean weekly sales per day, what do they get? About 134 cups? If they just use that average, they might think, okay, plan for about 134 cups a day.
But that 134 is misleading, isn't it? It's being pulled way up by those huge Friday and Saturday numbers. The median sale, the middle value across the week, is probably closer to 120 cups. That's a much better picture of a typical midweek day.
And the spread must be huge with those weekend spikes and the Sunday dip.
Exactly. The standard deviation comes out high, around 41.8 cups, and the coefficient of variation, SD divided by mean, is about 31.1%. That's a large relative spread.
So that high CV, over 30%, is the real action item, isn't it? It screams, your demand is not consistent. If the owner staffs or orders coffee beans based only on the 134 average, they'll be totally overwhelmed and run out on Friday, Saturday, and then have too much staff and old coffee sitting around on Sunday and Monday.
Totally. The high variability revealed by the SD, and especially the CV, tells them they need a flexible plan. Staffing needs to change day to day. Ordering needs to anticipate those peaks and troughs. So again, it comes back to choosing the right tool for the job. Mean versus median tells you about skew. SD versus CV tells you about absolute versus relative risk or consistency. You need to know what question you're trying to answer.
It really highlights that statistics aren't just about the numbers themselves, but what those numbers reveal about the underlying reality.
That's the core lesson. Understand the tools, but more importantly, understand the context and the question.
So to leave you with something to think about, let's bring it back to that idea of mean versus median and outliers. If you had to pick one number to represent the typical American income for, say, a news report or a policy discussion, which measure would you choose? The mean income or the median income? And maybe more importantly, why does the likely huge difference between those two numbers tell you far more about income distribution, about inequality perhaps, than either number could tell you on its own? Something to mull over. That's your deep dive homework for this week.